Okay, upwards and onwards, or depending on at which point in time you're looking at this stuff. I want to do question number 6. Question number 6. And the question asks us, does this point 1, 0, 2, 1 lie on the line through 5, 10, negative, where'd it go? I can remember, negative 1, 4, and let me write this down and I'll go over the question. Negative 2, 1, 1, 0. Negative 2, 1, 1, 0. So here are 2 points. It's a 4-dimensional space, but nonetheless, two points. There's one line that goes between them. Is this line on that line? Certainly, there are probably 3 or 4 different ways to work this one. But the way that occurs to me at first is that we're given 2 points. And I want to calculate the direction vector between those 2 points. Once I have the direction vector between those 2 points, I can write the equation of the line, and that will be a point on the line plus the scalar multiples of the vector between the 2 given points. And then we can see if we can solve it to get this point. So how do we get this point? Let's say this is the point right here, and this is the point right here. And maybe I should label these. I don't know, it doesn't really matter, but let's call that capital P. And we'll call this capital Q. So this right here is the vector P, Q. How do we get PQ? The direction here in this particular problem doesn't matter because the scalars can make it go either way. But just for the sake of consistency, remember this looks like this. If you want the arrows to go in, that direction, from P to Q, you take Q and subtract P. So to get PQ like this, we would take Q and subtract P. So let's see, negative 2 minus 5, negative 7. Now I should really write this like a vector now at this point, like that, or with the brackets, either way. Now I'm making a big giant mess out of the whole thing. But anyway, here's P. I'll write it like this. Negative 2 minus 5, negative 7, 1 minus 10, negative 9, 1 minus negative 1 is 2, and 0 minus 4 is negative 4. So there's the vector that goes between them. And so the line itself, whatever this line is right here, it's really that line, but then we're adding this, some vector that's already on the line. A vector is on the line. Well, the end of the vector is a point which is on the line. And so what we have to do is take a point on the line. We have 2 of them. Let's take this one because the equations look easier. And let me write it like this now. Negative 2, 1, 1, 0, plus all the scalar multiples of that vector. Negative 7, negative 9, 2, negative 4. And let's say R, where R is a real number. So if I wrote the whole thing out, it would look like this in set builder notation, such that R is an element of the real numbers. How do we tell if this is a point on this? We'll have to be able to solve the following. 1, 0, 2, 1 is equal to, from this, negative 2, 1, 1, 0, plus negative 7, negative 9, 2, negative 4, R. We have to be able to solve that for R. If we can, yes, this point is on that line. If we can't, no, it's not. So let's go ahead and do it. Let's look at the x coordinates first. We'd have 1. We'll have to equal negative 2 minus 7R. And from the y coordinate, 0 is equal to 1 minus 9R. And from the xyz, the z coordinate. I mean, I didn't really label these, but I guess xyz, w might be a nice way to do 4 dimensions. So 2, this is the z coordinate, equals 1 plus 2R. And then finally 1 equals, there's nothing there, so negative 4R. Now, if we're able to do this, look at the last one right here. This would tell us that R has no choice. It has to be negative 1/4. If negative 1/4 works in these 3, the answer is yes, it's on the line. If not, the answer is no. So let's give it a try. Put a, I can see it's no already, I think. Put a negative 1/4 in here, plus 1, you don't get 2, so the answer is no. I don't think any of those would have worked. Yeah. So unless I made an arithmetic mistake, which I don't think I did, the answer is no. Okay. So that was question number 6. I feel like I already did that on one of the other videos, but I guess I didn't. Okay. Hey, let me see if I can get number 7 done here. I'm always afraid now that if the videos run very long, I'll get my error message. The error message might as well be, hey, people don't like long videos, so hey, dude, don't make long videos, but that's not really what the error message says. Okay, so let me do question number 7. Number 7. And number 7 reads, give the vector description of the plane determined by the point 0, 1, 2, 3, 1, 0, 3, 2, 1, 0, 3, 2, and there should be one other point to get a plane out of this. 1, negative 1, 4, 1. Okay. And 1, negative 1, 4, 1. Okay, so there are 3 points which determine a plane, or an R4, but that really doesn't matter for our purposes right now. How do we get the plane? Again, there are many, many ways. One way to do it would be to write down a system of equations and unknowns. But let me take a different approach on this one. Oh boy, there really are several different ways to go about doing this, and the books chronicled them all. I'm afraid this video is going to run long. Maybe let me lay out the ways, and maybe I'll start. Now, why is my camera going out of focus? It's preposterous. There we go. One way is to write down a general equation of a plane in R4. Put these points in that equation and solve for the coefficients. That just sounds completely messy. We've done that. I don't know if I like doing that. Another way is to get 2 vectors like this. 2 vectors. Find the cross product. The cross product will be normal to the plane. And then maybe we should do it that way. I was thinking of doing it a different way, but let's go ahead and do it that way. It still involves some messy stuff. We have to find a cross product, and we have to find 2 vectors. So let's call this the vector P and the vector Q. And maybe I should have labeled all these things up here. Let me label this the point A, and this the point B, and this the point C. And how about if we have that as the point A, and we'll have this as B, and this is C. And so then really we could say this is the vector B, A, B, like this. And this will be the vector A, C, like that. And recall that this will be B minus A, that vector. And this will be the vector C minus A, like that. So we need to calculate B minus A and C minus A. So let's go ahead and do that. So this vector B minus A, where's B? B will subtract this, so we'll get 1 minus 0 is 1, and 0 minus 1 is negative 1, and 3 minus 2 is 1, and 2 minus 3 is 1. So there's that vector, and then we need the vector C minus A, like that, which is, where's C? C is here, so 1 minus 0 is 1, and negative 1 minus 1 is negative 2, 4 minus 2 is 2, and 1 minus 3 is 2. Now we need to find the cross product of these 2 vectors. So let me go back to writing it like this, a little more compactly, cross AC. And this will give us normal to the plane, and it will immediately, bam, give us coefficients in the equation of the plane. You know what? I may end this video right now because I've just done a terrible thing. And maybe it's good, it's a good teaching moment, right? The cross product, as we have it laid out, only applies to R3. So this cross product approach, it's no good. I went down the wrong road. Fine, let's back up. Let's take the other approach, which actually might be easier. Anyways, I had briefly talked about the idea of a span of 2 vectors, but I can't believe I just erased those. I want those vectors back. Oh my gosh. Let me see if we can get them really quickly here. I'm going to want those 2 vectors back. So let's get B minus A and C minus A. Let me get those two vectors back. Let's see, B minus A, what do we have here? So let's see, 1 minus 0 is 1, 0 minus 1 is negative 1, 3 minus 2 is 1, 2 minus 3 is 1. I don't feel like that's what I had written a minute ago. Let me see. 1 minus 0 is 1, 0 minus 1 is negative 1, 3 minus 2 is 1, 2 minus 3 is negative 1. That should be a negative 1. A negative 1. And then for C minus A, 1 minus 0 is 1, negative 1 minus 1 is negative 2, 4 minus 2 is 2, and 1 minus 3 is negative 2. There's something interesting. I think these numbers here are just coincidental. They look like there's some kind of a pattern there, but I don't think so. Okay, we have these two vectors. Now, if you take all possible scalar multiples of these vectors, right? Look at a scalar multiple here. It goes out, or it goes back, or it goes in that direction. Same thing here. Then if you add scalar multiples together, what do you get? You can use the parallelogram and you get vectors that look like this. And, you know, for all possible linear combinations of those two vectors, you get the entire plane. So what we need to have is all possible linear combinations of the following: 1, negative 1, 1, negative 1. Let's say I'll kind of use maybe the letters our book does a lot, S and T. And the other vector is 1, negative 2, 2, negative 2, say T. We need all those possible combinations, but we do have to be careful here because look at this. As I've left it like this, if you choose S and T to be 0, this would always go through the origin. Now, this may not go through the origin. What we need to do is add on a particular point, which we know is in the plane. Again, I've said this several times now, but it's very much like the y equals mx plus b. M is the slope. This is really the analog to the slope, the m. Now, the b is the y-intercept in the case of y equals mx plus b. It may not be over here, but I can choose any one of these points to be a specific point on the plane. So I'll just choose A, 0, 1, 2, 3. Notice now, if you choose S and T to be 0, this is the vector that you get. This vector is on the plane by definition because we were told it was on the plane. Okay? Now, right here you go, boom. That answers the question, except the question had a second part to it. And the second part is the origin on this? How do we know if the origin was on it? Well, here's the origin. Well, the origin is the vector 0, 0, 0, 0. X would have to be 0, and that would have to equal 0 plus S, 1 times S, plus 1 times T, T. And then 0 would have to equal 1, well, minus S, minus 2T. And then 0 would have to equal 2, let's see, we're on the third one, which is plus S plus 2T. And then the final, maybe XYZU or XYZW or whatever we're calling it, but 0 would have to equal 3 minus S minus 2T. And the question is, are there values of S and T such that all 4 of these are true simultaneously? Well, let's see. Let's simplify this a little bit and see if we can figure out whether or not that's the case. Look at this first one here. Let's see. S plus T equals 0. From the second one, we could say S plus 2T equals 1. I'm just simplifying this, right? So S plus 2T would have to equal what? Negative 2. And we've got problems right there right away, right? Look at that. But let's just, for sense of completeness here, S plus 2T equals 3. Well, S plus T cannot equal 0. Oh, sorry, S plus T, but S plus 2T cannot equal 1 and negative 2 and negative 3 all at the same time. So that cannot happen. And that means that this plane does not contain the origin. Notice I don't really know how I could graph this. If we have a plane in 3D, we really could attempt to make a graph and visually inspect it to see if the origin is contained in the plane. Here, I really don't know how to go about doing that. Maybe I'll have to think about it. I don't know. But at any rate, this describes a plane in R4. Is the origin a part of that plane? No. And just, it's the end of the video, but look, stop and think about it. If you choose 3 points, now I don't know if those are randomly chosen. I honestly can't remember if I got this from the book or if I changed the numbers. I don't remember. But let's just say I randomly choose 3 numbers, 1, 2, 3. Except for that unlikely event video that I published, first off, the odds of the 3 all being part of the same line are slim to none. And so you get a plane. So if I get 3 points, I'm almost always going to get a plane, right? There's going to be some plane. I don't really know how to indicate this, but the plane contains that triangle. But at any rate, it contains the span of these 3 vectors. If you chose this randomly, what are the odds that plane is just so happen to going to slice through the origin? And the answer is, wow, that was a really awkward sentence. But the probability seems to be preposterously low. So I am not surprised that it does not contain the origin. So that's no. Okay, so I'll come back and do the remaining questions in a follow-on video.